have fun. Yes, welcome to the AI4EU Cafe for live presentations around AI. Today, I have the pleasure to present you Nicu Sebe, professor in the University of Trento in Italy. Hello, Nicu.
Hello, everyone.
Hello.
Thanks for inviting me.
Yes, pleasure. And Nicu will present his talk, Image and Video Generation, a Deep Learning Approach. This cafe session is a cross-project collaboration between the Horizon 2020 European Research Project, AI for Media, and AI4EU. My name is Carmen McWilliams, and I'm the moderator and organizer of this cafe. And I am the director of the company Grassroot Arts and partner in both research projects in AI for Media as well as AI4EU. So important as always, take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, each speaker expresses her or his personal view and opinion. This is not necessarily the official AI4EU or AI for Media project opinion. So, and what's this AI Cafe about? It's an online forum to gain insight into the European AI scene. Participants get the chance to share knowledge and experience and meet stakeholders from various areas of AI research and application. And as you know, welcome, great that you're all here, and it's interactive. We need your questions, so if during the presentation you have some questions for the speaker, please write them down. There's on the right side, there is a panel, and you can write there your questions, send it to us, and I will read it afterwards to Nicu. So, after the short introduction, I will now introduce Nicu himself. Nicu Sebe is a professor in the University of Trento, Italy, where he's leading the research in the areas of multimedia information retrieval and human-computer interaction in computer vision applications. He received his PhD from the University of Leiden, the Netherlands, and has been involved in the past with the University of Amsterdam, the Netherlands, and the University of Illinois at Urbana-Champaign, USA. He was involved in the organization of the major conferences and workshops addressing the computer vision and human-centered aspects of multimedia information retrieval, among which as a general co-chair of the IEEE Automatic Face and Gesture Recognition Conference, FG 2008, ACM International Conference on Multimedia Retrieval, ICMR 2017, and ECM Multimedia 2013. And he was a program chair of ACM Multimedia 2011 and 2007, ECCV 2016, ICCV 2017, and ICPR 2020. Not easy to read. And he is the general chair of ACM Multimedia 2022 and a program chair of ECCV 2024. Currently, he is the ACM SIG Vice Chair, a fellow of IAPR, and a senior member of ACM and IEEE. So, welcome, Nicu. This is impressive.
Thanks a lot. Right. So,
we are for sure talking to a very important person here. So, I give you now the floor to present yourself and also what you will tell us today. I will now share with you the presenter role. One moment, so you can try out to share with us your presentation.
Okay. So here is my presentation. Can you hear me? Can you hear? Can you see it?
Yes, I hear you. I see you. I see the presentation. Everything is perfect.
Perfect. Let me try to see how I can skip. Okay. Okay, good. So I'm going to talk today about a subject that I've been involved for many years, and this is image and video generation. Of course, it's not my work alone. It is work done by several collaborators, several former students, postdoc, and so on. So here it's a list of people that have contributed to some of the topics that I'm going to present. But before that, let me start with a little bit of history. And this is my personal history into, let's say, image and video generation. Right. So I have a few videos So this is, let's say, starting with, this is around 2008, so it's about 13, 14 years ago. Just for you to see a little bit how clumsy all this application were, right? So practically here, what I was doing, I was putting a face mask that it would be a face taken from a single image. That was my former PhD advisor, Tom Huang from Urbana-Champaign. And you see, it's really looking like a mask. And I would just move my face, and then the face of Tom would move together with my face. Okay. It is for that time was quite impressive. Of course, right now you will see it's it's clearly obsolete. Okay. Later, so this is about 2018. So this is something done on a mobile phone. So this was an application done by a former student of mine. So you could put some funny things on your face in that time, and you can also do exactly the same like before. Right now, you can see that the mask is much better. Also the lighting condition and the hue stuff, it's much better, right? So we can still see it's a mask, but it's definitely working much better than it used before. Well, nowadays it's something like so. This is what it was. This is an application done by one of my students. Practically, this is a copy of my photo on the web page, and practically what my student did was just using a driving video, and then it was just animating my face to copy the same movement as the guy in the video. Okay, you see it's working pretty reasonable, even though on the right hand side you have a static image, and of course there are some small artifacts in the background. What can you do nowadays? And this is a video that was I took from the internet. It was somebody was using our software to animate these faces. So the one in the center, it's a driving video, and you are going to see all these funny characters being animated. I hope you can also hear the music. Okay, so let me put back my microphone.
It's super fun.
Okay, right. So the idea is here that, of course, you have all these static images that are animated by the driving video. Let me play it again. So that's this time without the sound. But you can see that also the eyes are moving. Also the mouse is filled in, so it's not looking like hollow like it was before. Okay. And what is interesting is that this video was not created by us, but was created by somebody who really took our code and was just, running it and then animating these characters. I will go a little bit into details in the next slides. Okay, so what I'm going to talk today about, so it's going to be first about generating images and videos. This is using deep generative models. I will start with generating facial expressions for a particular from a particular face, and this is the lower part. Then I will talk about generating different viewpoints. This is images of people. So if you start with a view on the right and you have a target pose, you can generate the way this particular person will look from that particular pose and viewpoint. Okay. Then I will talk about in details about how you can animate a particular static image using a driving video, right? This is an arbitrary object animation without 3D modeling. So it's not only faces, but also bodies and robots that you are going to see. And I will finish with some recent work. It's on playable and multimodal video generation. Well, a few of our publications, so just to have a little bit of a reference on where we publish this. So this is the first work on landmark guided diverse smile generation. So the idea is very simple. So you want to generate a sequence of facial expressions, smiles in this case, condition of different labels, right? You have a neutral face. You have a conditional label, so you tell what sort of smile you want to generate. It could be posed, creepy, nervous, and so on. And then practically what to do, you generate a smiling video out of it. Okay, so you just generate 3 different sequences of smiles. Okay, So you start from this face, you extract key points, and from there you generate different type of smiles. And you see here, they are all smiles, but they are different, right? So in one hand, on the upper part, where the eyes are closed, on the other one, the mouth is more open, and so on. Okay. So practically, what we want is to have this conditioning part using this conditional recurrent neural networks. We are using a one-to-many type of approach. So we want to have a push-pull loss. So push means that I want my smiles, so my facial expressions, to be as diverse as possible. Okay. But on the other hand, I want them to stay together within the same smile class. Okay. So I want them to be as diverse as possible within the same class. Okay. Also, it's quite important to preserve the identity. Right. So what we want to make sure that when we generate the video, it's still the same person. A little bit of details. This is the scheme that we did. Practically, we start by encoding the landmark images and generate a sequence of landmark embeddings. So here, practically, what we are doing, we are extracting the landmark of the face, and then from there, using the conditional LSTM, we are generating this. Using the decoding part, we are generating different conditioning labels. Then we generate different landmark embedding sequences. I'm not going into details, but just to give you some ideas in here, I'm going to play some videos so you will see exactly how it works. And in the end, we translate each sequence into a face video, right? So what we do, practically, we do a texture mapping. And once we have the original texture of the face, we can just put it together on the generated landmarks, and then we are generating the sequence of the smiley videos. Okay. Well, some details I will just skip for matter of time. So what is important here at the end, we are using a UNet to be able to preserve the identity of the particular of the person that we want to animate. So what you can obtain in here, you can see several things. So if this is original sequence, practically what we do, so this is just for a reference, what we can do, we can have different modes in which we are generating smiles of the same person, but at having different characteristics. So you can have, for example, a wide open mouth. You see it's different from the original sequence that will be used for training. You can also have the closed mouth, for example. You can also have the closed eyes, and so on, right? So you can have this diversity in displaying the facial expression. And the good thing about it, and this is what we showed into our further experiments, was that this is good for data augmentation. So even if you don't have, let's say, enough training data, especially if you want to get to, let's say, spontaneous facial expressions, you can use this trick to augment your data, and then your training is going to get much better. Okay, so this is some example. This is comparison with the state of the art. There are different method that you have in here. You can see a few artifacts for our competitors. So here you have some strange stains you get on the face. In some cases, you are losing the identity, and so on. So let me play the video. So practically here, what we do, we have the sequences that are generated from neutral to the smile, and then going back to neutral. Right, so you can see here the differences between different types of smiles, so spontaneous and pose smiles. Of course, in the pose, you have a much larger amplitude of the facial expression. Okay, and here you can have different type of characteristics. This is done really in an unsupervised way, so we don't tell the network what sort of characteristic we want to do. The network is just learning from the example that we have in the training set. So it's learning what sort of deformation you can have on the face, so that you still keep a good display of the facial expression. We've been doing it for smiles, but you can also do it for a lot of other facial expressions. Okay, so here it's a simple example in which we are doing practically a video generation, starting from a static image and a neutral static image in this case, and a conditioning label. Okay, Another thing that we've been working on was doing pose-based human image generation. So there is already, you probably know, there is the classical approach by, so this is a work done by Ben Schiele, Tina Tuttelard, and Luc van Gogh and their students. Practically what you do, you just have an original image, you extract some key points, including their heat maps and so, you are using a generator, you are doing a prediction, and then practically what you do, you have a loss in which is telling you how different this prediction is from the ground truth. And from there, you are using a discriminator, and you detect if this particular image generation, if it's fake or it's real. Okay. Usually, what we do have in general is that in a rigid scene generation task, the local structure of the conditioning and output image structure are well aligned. While in our case, we talk about the firmable object generation task, the input and the output are not specially aligned. So the main problem in this case is that if you just take a particular, let's say, part of the image and you put it to the network, and then you are looking at the output of the network, you are going to see that it's corresponding to a wrong side of the value, right? So practically what you need to do, you need to consider a deformation model inside. And this is exactly what we did. So then for each specific body part, so let's say this one of the upper leg, what you do, you compute an affine transformation, FH, right? And then you are using this FH, so you are moving the corresponding feature map content from the source part to the target part, right? So practically you are making the connection between this XA and this XB. Okay, so in the target stream, you have a target pose. You are using a heat map using Gaussian blurring, right? So just to allow for some small variation around the particular position. Then you are using these feature maps that are shuttled by the skip connection from the HV stream, from the target stream. And then you are obtaining these feature maps directly using up convolutional filters applied to the previous layer maps. And then you have the source stream, in which here you have the joint location in the XA and the heat map are spatially aligned. This is by construction because this is it's extracted from the source stream. Then in the HB, so in the upper part, this joint location may be far apart from the original stuff what you have in there, right? Then this means that you are not concatenating this HB with the other input tensors. But what you are doing at the very end, you are computing these deformed tensors that are shuttled by these deformable connections from this HXA HI stream. So practically here, what you are doing in the target stream, you get the correspondence between the parts, and you are generating the corresponding parts according to this correspondence. Okay, so just to give you some examples. So this is the original image, this is the target pose, and this is how we generate it. This is the ground truth. These are different examples of competitors, and this is our generation. You see it's not as sharp as you would expect, but an important thing is here that we are also able to generate, for example, a backpack. It's not perfect, but at least you can still see the patch into here. This is another example. Also here you can see this is the side view of the person. The target pose it's from the back, and you can still generate quite well even the backpack, right? So this means that we do have a few examples of backpacks, and the network is able to learn what will be the appearance of this particular type of backpack. Okay. This is an example on the deep fashion data set in which you have quite a large change in scale between the source and the target. You can see that we are also reasonably able to reproduce also the texture. Let's say the Rolling Stone logo in here. Also here you have quite some good texture generation also for the shirt and for the trousers. Okay, then it's working pretty reasonable, even if the target scale is completely different from the one of the source. Of course, it's not always working perfectly. So you may have some errors in the pose estimation. So here you can see some examples, right? Also, when you have some ambiguity in the pose estimation, you can see here it's not very sharp and it's having some troubles, especially because the background is quite complex. So there is a bicycle around and it's having some trouble to generate this. And you also have some rare object appearance. For example, this purse, we don't have enough examples into our training data set, so this one is not able to be reconstructed very well. Okay, so here it's making a lot of time. But in general, we are able to do it quite well. And right now, we've been working also on generating not only single images from different viewpoints, but also as long as a pose is rotating and it's animated, you can also generate animated different viewpoints of the same object. Okay, now going towards image animation, and this is something that has been very popular. So my student Alex Yarokin was the one presented this first order model. And since then, it has been used by many people, and it's getting one of the, let's say, the popular ways of creating deepfakes. Okay, so actually what we try to do, in general, what people will do appearance transfer, right? So you detect the pose in each frame of the driving video, and then you apply our pose-based image generation with the source image and each detected pose, right? So this was what I presented you before, right? Here you can do it for every single frame. The problem is that you are requiring a detector, right? So you need to detect a particular, let's say, person or object and so on. And it does not work well when the shapes of the object are different. Let's say if you are going from short to tall person. So what we propose in our work here is to use unsupervised transfer motion. So this means here that we are practically using now the motion transfer in order to animate objects. Another thing that is important is that we are not making any assumption on the type of object we are animating. The only assumption is that the motion of the particular object we are animating is compatible with the one of the driving video, right? You cannot just animate a face to let's say to move like a horse, like running of a horse. That doesn't make any sense. Okay, so for this, what we did, we proposed this monkey net, which is image animation with moving key points. We have the alignment problem, right? If you start with the first frame and you want to go to the animated frame, you see that there is a big displacement between the points that you want to animate, right? So in order to do this, what we do, we have a motion-specific key point detector, right? We have a motion prediction network. This is the delta. Then we have a motion prediction network, and an image generator G that reconstructs the image X prime from the key point position, and the optical flow is computed by M and used by G to handle misalignment between X and X prime, right? We are learning the model with the self-supervised learning scheme, right? So this is the motion prediction. So from the appearance of the first frame and the key point's motion, practically what this network M does predicts a mask for each key point and the residual motion, right? So it predicts what part of the body is going to move, and then what's going to be the residual key points motion for particular body points. Okay, and then at the testing time, the model generates a video with the object appearance at the source image, but with the motion from the driving video, right? So practically, we are transferring the motion between the source image and each driving frame, and we are providing the generated with a relative difference between the key points. So let me show you a video here in which we show you what it is. So the colored points are the points that are identified as being representative for the motion. Let's say for the face, they are not necessarily related to the anatomical part of the face, but it's most of the time you see are related to, let's say, the eyebrows, the mouth movement, and so on. On the body, it's a little bit more clear because it's usually they are extracted in an unsupervised way, mostly to let's say the motion part of the body. You see, so it's kind of related, especially on the body, it's related mostly to the joints, right? Because these are the ones that are moving. Okay, let me move a bit further. So here, practically, what you can do, you can animate, for example, a robot arm. So you have a static image up here, and using a driving video, you can just animate this robot arm to capture the motion of this robot. You can also animate, for example, different characters. This is for the deep fashion stuff. You see it's working pretty reasonable. This is, the data set is called Tai Chi. Here, the difference is that the background is far more complex. In some cases, when the background is very complex, we are having some troubles. You can see that it's not reconstructed very well. We can also animate, let's say, cartoon characters, right? So you have a driving video, and you can animate these guys. You can be horse to horse, but it can also be cat to horse, for example. And you see it's working quite reasonable, and the animation is different. And of course, what you've seen before, you can animate faces. What you can see here, when the head pose is quite strong, it's having a little bit of deformation. It's also because we are not using any 3D information in here. It's only using appearance. And so what we are doing right now is trying to incorporate 3D information so that we are not getting this artifact like you see here with Mona Lisa when it's it's animating, let's say, it's animating by Obama's face. And as I said, this work was quite popular, and there were many people taking our code and were using it for animating, well, their faces or their characters. This is a part of the video that I took from the YouTube. It is a video done by a guy who is kind of a technology scouter. And practically what he did is he took our software and then practically he's trying to explain it for the public what the software does, and he's also testing it with animation. Let me play it a bit.
Dear fellow scholars, this is 2-minute papers with Dr. Karo Zsolnai-Fehér. It is important for you to know that everybody can make deepfakes now. You can turn your head around, mouth movements are looking great, and eye movements are also translated into the target footage. And of course, as we always say, 2 more papers down the line, and it will be even better.
I'm not going to let it play all together. He's explaining how the method works and so on. Let me go to toward the end.
And inexpensively, and they don't require conferences and inform in the world. Note that these talks and consultations all happen free of charge, and if they keep inviting me, I'll keep showing up to help with this in the future as a service to the public. The cool thing is that later, over dinner, they tend to come back to me with a summary of their understanding of the situation, and I highly appreciate the fact that they are open to what we, scientists, have to say. And now, please enjoy the promised footage. Dear fellow scholars, this is 2-minute papers with Dr. Karo Zsolnai-Fehér.
Okay.
It is important for you.
So you can see that the guy practically what he did, he took our software and then he created his own video, and it's animating different characters. This is from Game of Thrones and so on. I mean, you can play around with the software, and this is completely free, and it's working pretty reasonable. Okay, another thing that we've been working on is trying to, while before we were animating the entire face, we were trying to look into if we can do, let's say, only part segmentation, in the sense that if we can animate only parts of the face. Let me see what this means. So practically, we want to leverage motion to train a segmentation network without annotation, right? So we want to get a source frame, a target frame, and we want to use the motion to segment part of the body so that we can capture, let's say, only parts of the motion that can be done, with this framework. The good thing about this is that you can then replace a particular part, and you can just, for example, animate or in paint only some particular characteristics. So practically at the testing image, you just do segmentation and you know how this is going to be animated. Right? So we have in the segmentation model, we are predicting a segmentation map from the source to the target and the affine motion parameters. And then we compute a background visibility mask. So we tell which part is going to be, going to be animating. Then you have an optical flow, and we are reconstructing the target frame by warping the features of the source frame and masking the occluded frames. Okay, so this is just an example. I'm going to play a bit. You see the segmentation maps from. So this is the input. This is the obtained segments. And what you can do with this, let me play a little bit further. You can try to animate only parts of the face. Right. So for example, here you want to take the hair of Tom Cruise and you want to put it on top of this guy, and you animate it, or the hair of this guy. And it's quite reasonable. You can also take, let's say, the glasses from the Scarface and you put it on this guy, or you take the nose of Michelle Obama and you change the nose and the eyes, and you animate it here. This is again the eyes, the lips, and so on. Okay, so practically here, what you are using, we are doing motion segmentation. We are getting the segments that we know that they are moving, and then based on that, we go into the original image and we take that part that can be used for doing animation. So this is, you can take the beard and you can put it on top of this. Whatever, glasses, hairstyle, and so on. Okay, so I would like, in the remaining 10 minutes, I would like to talk about two different, let's say, new things that we've been working on. So one is playable video generation. So this is the work done by the students in my group and the students of my colleague Elisa Ricci. So practically the idea is, it's very simple. You consider a set of video depicting an agent acting in an environment, let's say a tennis player in this way. And what you want to do, and here you have no annotation, practically what you want to do, you want to learn a model that represents the observed environment, and you want to allow the user to input the action through a controller at the testing time. So practically what you want to do, you want to let the user indicate how this object should move, so the tennis player, and so the player can move left and right and up and down, for example, but you want at that particular location to reproduce the motion, the natural motion of the player in that particular location, right? As would be this guy is really playing tennis and is really going towards the net. Yeah, so practically what you want to do is to produce a video where the agent acts according to the action specified by the user. You can see here, you can move to the right, you can also move forward, and so on. Right, so how do we do this? Well, first of all, you sample an input sequence and use an encoder network to extract frame features. Then you pair successive frames to infer the action that was performed by the agent in corresponding transition using an action network, right? So you just look at the two successive frames. On top of that, you are given the frame features and the action. You are using a recurrent model to produce features representing the successive states. And then you translate this one back to the image using a decoder network. Okay? And what you do, this is for extra supervision, you can encode back the produced frame using the encoder and the action network, so that here you are also including the residual network, that is the residual motion that you obtain. Right? And in that way, you can also impose different self-supervision losses of the frame friction, and the produced action. And you are using a mutual information maximization load between the action and the reconstruction action as a driving loss for action learning. Right? And then the model is enrolled over the whole sequence. Well, some details, I can skip this one for the sake of time, but what you can do here, you can see here, you can learn a wide range of actions. Right? For example, this is the guy going towards the net. This is going left and right. what you see is that he is also not only moving the body, but it's also moving the, it's rotating in such a way, for example, to hit the ball, you know, when it's moving to the left or to the right, okay? And this kind of actions are quite plausible, right? So practically the user, it's indicating how you want to move this guy, and then this guy, it's moving accordingly in a natural way, depending from the starting frame of the action. Yeah, so this is the same type of stuff. You can also do it for the robots. And here, according to the indication of the user, you can generate the motion of the action as it would be in a natural way, moving by the robot. Right. What you can also do some sort of interpolation between the actions. So you can, even if you generate only this action 6 and action 7, and action 6 that the player is staying still, you can generate something in between, and you do have frames also on the diagonal part, right? So you can also get somebody moving to the left, but also moving towards the net, and so on. Okay, so it gives you a lot of freedom into generating this type of action. So this is just a simple demo in which a user can use some of the keys from the keyboard to generate. And here you can see how the player is generated, and have a look at how also the body part, the upper part is generated. And here we are moving from different type of actions. So this is action number 7, it's going to action number 6, and so on. Okay, and now it's going to go towards the net, and so on. Right, so here it's really what we don't have yet, and this would be something that is of interest to us, is to generate the video according to the interaction between this player and, let's say, the other player or the ball. Okay, so okay, you can also make the guy move towards the net. And you can also make it disappear, right? If it's going further, it will just realize that there is nothing there, and then the guy is kind of really vanishing. Okay, so the last thing that I want to discuss is music-guided dense video synthesis. So this is kind of, let's say, similar to what we did before. The only difference is here that we are learning the motion patterns from the audio part, and what we are doing, we are generating moving stick models that are dancing according to the music, right? So practically what we do, we have some music feature extraction network. We do have 2 networks. So one is a self-frame graph spatial attention network. The other one is a cross-frame temporal graph attention network. So practically one, it's generating the appearance. The other one, it's looking at the temporal domain. And then what we do, we have 2 stages. So one is music to skeleton translation, right? So you are generating the way the skeleton is going to be moving according to the music. And then in the second stage, we have a skeleton to dance translation, in which practically we do the texture mapping, and we are putting the texture of the body onto the skeleton, and then we are generating the animated body. Okay. So in this one, practically what we do, we are using a self-supervision framework. We are learning the connecting between different body parts and one, let's say, pivot part, in this case, the one in the center of the body. And we are doing a weighted sum of all these interactions, and this is going to be generated. In the same way, you can also use different frames, so you get the same joint at different time instances, both in the past and also in the future for learning. And in this way, you are doing again a weighted sum, and you are obtaining the generated body skeleton. Let me try to play the video. So you can have different type of, this is Ballet. Then we do have, try to skip a bit forward. We have K-pop. We do have also comparison with different other methods. And you see it's working pretty reasonable. The music is, the generation is quite plausible. I don't have the video with animated body, but you can imagine that now that you can easily take the texture and put it on top of this stick model. Okay. So this is more or less what we've been working into this area. And let me conclude a little bit by indicating some of the limitation and possible extension of our work. So one of the main issues that I already pointed out is the fact that we do have some issues with the 3D movements, right? So what we are working right now is to incorporate the modeling of 3D key points and other 3D information, okay? So far we are animating single objects. So the goal is now to animate multiple objects, and we want to consider also interaction between them. I was telling you, for example, for the tennis player, you could also consider the two players, and they would, let's say, influence each other. So the animation of one would influence the animation of the other one, and so on, right? So in the tennis, for example, in a tennis game, the players are not moving randomly on the field, but they are directly interacting. But you can also consider something like, dancing or boxing or other kind of things in which you can try to understand an action and you can try to understand the reaction of different people. Right? And then what we can try to do, you can also consider doing the video-to-video translation in which you can consider, for example, generation of different domains. So going from real to, let's say, to videos or to sketches, and so on. So imagine that you now have a video sequence and you are generating some kind of comics book out of it. Okay. And in the end, we are not doing it, but of course, there could be some possible ethical issues, right? Because people may use this particular technology to create deep fakes. Of course, we are on the good side in the sense that we realize that the method is not perfect, and getting perfect deep fakes it's difficult. But of course, we need to consider also research into doing deepfake forensics and to understand if, for example, a particular image is real or it's not, right? Because the technology is getting better and better. Another limitation that we do have is that so far we are generating not so high resolution videos, but we are working into getting better and better resolution. So I expect in the near future, we could be able to generate quite plausible videos, and I think this could be quite useful for many applications. Okay, I guess that's what I wanted to talk about today.
Yes. Hello. Thank you very much, Nicu. This was a deep insight. Great.
Thank you.
Thank you. Very exciting work, I must say. And as I invited you as a speaker, I am also allowed to ask the first question before I let the audience ask you. I'm especially interested in the dancing, because I'm involved in a FET project. I'm the project manager from Carousel, which is about dancing and 3D dancing avatars and possibly AI animated avatars who can dance to music. And here I really would like to know what are these issues which you say, what are the issues with 3D movement? I'm really interested. What are the issues there? Is it possible to translate this to 3D modeling, and what are the issues?
Well, I guess I would say in general for this video generation part, the main issues are related to the available amount of data, right? So if you are able to get a good data set in which you have good annotations, let's say 3D avatars that are moving and so on, then I guess you can learn, the network can learn very well also some of the, let's say, the 3D movements quite well. Another issue with 3D would be, of course, and this is also for music to animated videos, is that there is still some ambiguity. So what you can generate there, you generate a plausible solution, but it's not the only one, right? Because even on music, right, when you dance, you can dance still keeping the rhythm, but you can dance in different ways.
Yes.
So what you can, so again, it is not a one-to-one solution. I mean, this is also for the 2D, but in general, it's getting even, in 3D, it's getting even more complex because let's say if you consider rotations, can be rotation to the right, rotation to the left, and they are all plausible. And so you would have to somehow kind of learn this type of possible actions and then decide which one of the passes to animate. It's a more let's say possible one. It's a more natural one in many ways.
Yes. So you have to basically teach it what could be plausible, no? For example,
in many cases you learn it from the data, right? So you need to have diverse data, because if you have for example people rotating only to the left, the network will learn only that, and that's all. I mean, it will not know that you can also rotate to the other side. So you need to have a little bit of let's say diversity in your data, so you can learn different passes.
Yes. Okay. Thank you. This is very interesting. It's come from the audience. The next question, and that is here from Ahmad Hamoudeh. Hi, Ahmad. Sorry. Can you please elaborate on the computational power and the training time needed to develop each one of the mentioned models?
Okay, so what we do, we are using, let's say, GPUs. So we have servers with, I think if you get a server with, let's say, 4 to 8 GPUs, should work pretty reasonable. Training takes some time. I would say so far for learning a good model, it will take about a day. The good thing is that, so this is only for training. The good thing is that let's say in the testing part, it's practically real time. So it will take time to learn the models, but then once you have learned it, then the animation it's in real time.
Okay. Yes, and then comes from Essam Goda. Hello, Essam. The question is more general for us all. Would you share with the participant who asked for it your presentation, your PowerPoint?
Yes, I have no problem to share it. Yes, I can share it. Yes. So
here we ask you to send me or Nico your question that you would like to have. Basically you ask us and we will send it to you. So that's the point. And next question is, as we are both in AI4Media, this is a project we both are partners in. What are you doing? What's your role there? What are you doing there?
Well, my official role is work package 3 leader. So this is dealing with advanced machine learning techniques. This relates mostly, let's say, to the use of multimedia, right? So it's not only machine learning per se. So practically what we try to do is to understand, let's say, not only different ways of doing, let's say, transfer learning. There is learning at the edge. I'm thinking about the tasks that we have in there. We have the neural architecture search, but it's also about fusion of information. So I'm also involved into what is work package 9. This is related to the artificial intelligence digital academy, and this is on trying to provide to manage to the community, to provide the courses and tutorials as well as presentations like I did today. So there is also an IDA lecture series in which we are inviting people, and you can on different topics, of course, that are related, let's say, in general to multimedia, but also to AI, machine learning, and so on.
Yes, thank you. And I have another question. And so basically, as we are here in the moment in Europe talking a lot about trustworthy AI, and you before mentioned the possibility, of course, with ethical issues of deepfakes. I mean, it could be used for deepfakes. What can you give us, number one, an example, what in your eyes is trustworthy AI in the context of media? That would be great if you give an example. And secondly, how to prevent these kind of deep fakes. Is there any solution or idea or no idea?
Well, I mean, sure. Okay, so how to prevent deep fakes? Well, first of all, you need to understand how these deep fakes are made. And once you know that, then you can probably get also counter-attack type of method. And there are, let's say, companies like Snap, for example, because they are providing different filters and so on. So what they do when they are creating these deepfakes, they are putting a sort of a watermark, like a gadget on top of, somewhere in the corner of the video, so just to indicate, to tell everyone that this is the deepfake. About the trustworthy stuff, well, I think there are many examples in which people are using this. And let's say, for example, every bioidentification type of methods are already trustworthy, right? If you think about, on your mobile phone using, Face ID, also on the laptops right now, and so on. So I think these ones are quite robust and are working quite well. And I think slowly we are going to develop more methods onto that. I'm involved into a workshop at ICCB, which is exactly on trustworthy. This is computer vision, more like related to how you can do human-centric type of approaches that are considering also the privacy and as identity of people. And this is, I think it's quite an important aspect. And it's true that in the past, especially, let's say, AI and computer vision researchers were not so much concerned about it. But I think it's getting quite important at the moment.
Yes, thank you. So we are coming to the end of this nice session, and I must again thank you, Nicu, that you're here, and I will send you afterwards the recording. And for everybody in the audience, if Nicu allows, then it will be published in the AI4EU channel. You get the link to the recording. And I'll just announce the next cafe, which is tomorrow. So if you feel like coming back, there's tomorrow the speaker Joseph Baker Brunnbauer from Social Tech Lab, and he will talk about how to overcome the barrier to kick off trustworthy AI implementation. So that's trustworthy. So please come back tomorrow at 3 p.m. That would be nice. And else for today, I close the session, and thank you, Nicu.
Thanks a lot. Thanks, my pleasure, really.
It was a pleasure to have you here, and see you soon, hopefully in real, in one of
I do hope. I really hope. I mean, I think we all need to meet face to face very soon.
Yes.
Okay.
So, bye bye.
Bye bye. Thank you.